Hello, this is Mr. Huff, and I want to talk to you about the dolphin problem from the homework. It was the one, I think it said 8 minutes to solve. I wanted to go over this just so you know about a formula that's not included in your book, from what I can tell, and a way to approach this kind of problem. So, the problem gives you an example where a dolphin is jumping out of the water, and it goes so many meters, and you know the angle that it came out of the water, and it wants to know the launch velocity, the initial velocity of the dolphin. So we have our little dolphin, and he's a true projectile. He jumps out of the water and lands back in the water. We know this distance, we know this angle represented by alpha, and we want to know the launch velocity. So the first thing we need to look at is we are interested in what's happening in x. And if we look back on our notes, we'll see that x is equal to the velocity in x times time. This is just velocity as distance divided by time rearranged. And we also need to remember that if we know the launch velocity and the angle, we can find x. So we should be able to take the Vx and replace it with the launch velocity times cosine theta times time, and that would give us our displacement. And then we can use that to find the launch velocity. But now we have to deal with that time thing. Time is going to be found in the uniformly accelerated motion formula. Y equals the initial position in y plus the initial velocity in y times time, plus 1/2 at squared. If we start at 0 and end at 0 as far as y displacement, we can replace these two with zeros. And that leaves us with this nice tidy little formula. 0 equals the initial velocity in y times time plus 1/2 at squared. And if you look at this, we have v, the initial velocity times time, plus 1/2 at squared. We can factor out the t, or one of the t's, and get rid of that pesky square. That makes our life easier. And we can also replace acceleration with the negative value of gravity, 9.8 meters per second squared. And it's negative because it's going opposite of the initial velocity. Now we can rearrange this formula that's greatly simplified from where we started by adding 1/2 gt to each side. We get the initial velocity in y is equal to 1/2 g times t. Starting from that, we can rearrange that to solve for time by multiplying both sides by 2 and dividing by gravity, which is a positive value now because of the transition from negative to positive, moving it to the other side of the equals previously. Alright. We can recall that the initial velocity in y is equal to the launch velocity times sine of the angle. So we're solving for the opposite side of that trajectory here. So if we were looking at this, we would use sine to find the length of y right here. So using that value, we can substitute the initial velocity in y with v0, or the initial velocity, times sine theta divided by g. So far so good. Let's return to the x formula. X is equal to the velocity in x times t, or the launch velocity times cosine theta times t. And we just found that t is also equal to 2 times the initial velocity times sine theta divided by g. So if we put all of those together, we could solve this problem right now. You could replace the range, the x value, with a number. You can replace the theta with a number. And we know that gravity is 9.8. You could, at this point, solve it like a simple algebra problem, looking for the value of VO, or the launch velocity. But we need to continue if we want to understand how the world usually sees this formula. Starting from this, we can rearrange this to be a little more tidy by moving the launch velocity times cosine theta above the line that separates the numerator and the denominator. And then we can simplify even further by making it VO squared and then putting 2 times sine theta times cosine theta in a row. And then if we apply a little bit of trig, you're not expected to know this, but it would have helped in this problem. The law of double angles. So if you have 2 times sine theta times cosine theta, that is the same as saying sine 2 theta. It's mathematically equal. So now we end up with x equals the initial velocity squared times sine of double the angle divided by g. This is normally how this formula is shown in every textbook I've looked at, except for yours. And this is called the horizontal range formula. So the horizontal range is equal to the launch velocity squared times sine of double the initial angle divided by g. And you could rearrange this to solve for your initial velocity by isolating the initial velocity, so you would get g times r divided by sine 2 theta equals vi squared. So that's a quick walkthrough of how they derived that range formula and what you would have needed to do to solve the dolphin problem.